In chapter 3, we're talking about vectors and doing motion in 2 dimensions now. So chapter 2, we're doing 1 dimension motion. Now we're putting it in 2 dimensions. So this includes like throwing a ball in the air. It's going to go up and down and like forward. Okay, so straight line paths in chapter 2. This time we're doing paths that are curves, so 2-dimensional motion. So a ball arcing through the air is one example. And we're going to learn how to use vectors as our tool for studying this type of motion. So in the figure, we have the velocity vector v has both a magnitude and a direction, of course, because it's a vector. So the magnitude of the vector here is 5 meters per second. And the direction of the vector, we can see the way that the arrow is pointing. So we have our vector magnitude and direction. The name of the vector is here. It's a v with an arrow above it, and the vector represents the particle's velocity at this one point. If we have time going on, as time goes on, the vector might change direction. It might change its magnitude. So then the arrow would be pointing a slightly different direction, and it might be slightly longer or slightly shorter. Okay? So as we move through time, this vector might now be here, and it might have this orientation, and it might be slightly shorter, right? Okay, so that's kind of how things are going to go here. Now, as we work with vectors, if it's a displacement vector, then we have a straight line connection from the initial position to the final position. So as we'll see in this diagram here, the displacement vector for Sam, from Sam's house to wherever he wound up, is not caring about what Sam's path was. So here's Sam's path. He wanders around. You know, he's sleepwalking. So here he winds up right here. So what was Sam's displacement? So that's just going to be the straight line path from where he left his back door to where he ended up, slumped over against the tree stump. So there we are. There's where we found him in the morning. Okay, so that's our Sam's displacement vector. It's just a straight line connection from where he started to where he finished. So also, remember that vectors have the magnitude and direction. So in this case, it would be how far and what angle, okay? What direction was he pointed? So for this vector, we might say Sam's displacement was 200 feet and exactly northeast, okay? But generally we're going to figure out some angle, so it might be like 34.1 degrees north of east or something like that, okay? All right, so moving on. Sam's next door neighbor, Becky, also sleepwalks 200 feet northeast. Then her displacement vector d sub b, because it's Becky now, has the same magnitude and direction as Sam. So because the vectors are defined by their magnitude and directions, those two vectors are equal. So Sam is sitting right here, slumped over the table because he tripped and fell. And then Becky is also here. So those two vectors, because they have the same magnitude and direction, are exactly the same. I could pick this vector up right here and set it down on top of that vector right there. As long as I don't change the orientation of it, they're exactly the same vector. Got it? Okay, good. Moving on. Working with vectors now. So this is vector addition. We've seen this already, but we'll talk about it again. The displacement vector is the straight line path from start to finish. So if we displace twice, so first we go east and then we go north, this final position will be resulting, the displacement vector is the result. So this is called the net displacement. The initial displacement A plus the second displacement B. So in the picture, here is our initial displacement A, and then we have a second displacement, so we stopped here for a second, and then we displaced up here to B. Okay, so if we didn't know, like if I did that, and you guys weren't watching, but you did know where I started, and then you opened your eyes and you saw where I finished, you would draw this displacement vector right here. You'd say, well, that's all you did, okay? So, but I actually did do those two green ones instead, okay? That's vector addition. So I add these two green vectors together. Notice that they are head to tail, and I wind up with the raspberry sorbet flavored vector instead, okay? So that's how we do vector addition. This is vector A plus vector B gives me vector C. Put the two vectors head to tail, and you wind up with tail to head, where I started to where I finished on the other two vectors, gives me my resultant vector. It's pretty easy to do. Just where I started on the first one to where I finished on the second one, and that's my net displacement. Good? Okay. Moving along. It is a commutative situation. So what we mean by that is we can say, okay, I have these two vectors that I'm adding together. I can add them in either order, just like in regular math, 2 plus 3 and 3 plus 2 are the same thing. I can take those two vectors and I can add them together in either order. It doesn't matter. And I'll wind up in the same spot in the end. So I can go north first and then east, or I can go east first and then north, and I'll wind up in the same spot. Okay? So this is called the parallelogram rule. Two vectors can be added using the tip-to-tail rule, which winds up looking like a parallelogram if you do one and then the other, or the first one and then the second one. But then switch it around and do the second one and then the first one, okay? So I have vectors D and E that I have to add together. I can add D plus E first, okay, which would give me this part. Or I can add vector E first and then vector D, which gives me that part. And when I put those two together, vector D and vector E first, or vector E and vector D first, I wind up with this parallelogram looking situation, okay? And that's called the parallelogram rule. So it doesn't matter which ones I add together first, because either way I'm going to wind up with this like parallelogram looking thing. And where is the resultant vector? Right here along this diagonal. So, very nice, pretty straightforward. Also, notice that they're not really anchored down. I don't remember now if we are going to talk about that in a second or not, but this location right here is not anchored down. You can move that anywhere. So there's no set position for where these vectors start and stop. I can move them anywhere. Like I can start it right here, I can start it down here, and then go vector D and vector E, and then I wind up with, so I should be drawing arrows there, but, and then wind up with the resultant vector, okay? I can do it over here, vector D, vector E, wind up with the resultant vector, okay? These are all the same. This one here, this one here, this one here, this one here, those are all the same. There's no set location for where you start, okay? All right, so let's move on. Working with vectors and doing vector multiplication. So multiplying a vector by a positive scalar gives you a new vector with a different magnitude, but the direction has not changed, as long as it's a positive scalar. If it's a negative scalar, then the vector reverses direction. So, positive scalar, the direction stays the same, and I have changed the magnitude. So if the scalar is greater than 1, the vector has a greater magnitude. If the scalar is equal to 1, I haven't changed the magnitude at all. And if the scalar is between 0 and 1, then we have a smaller magnitude. I think you can probably understand that, right? If you've taken any kind of math anywhere along the way, you should understand that. This is just like a transformation of a matrix, for example, okay? So we have the length of vector B is stretched by the factor C, so that made it either longer or shorter. It just depends on if this factor C here is bigger than 1 or smaller than 1. If it's equal to 1, we're not going anywhere. We didn't change anything.
And subtraction.
All right, so moving on. So if we multiply by the scalar of -1, the vector has the same magnitude, but it's going to switch direction. So in this case, on the first drawing, vector -A we started with positive A, so that was this guy. And then negative A just reverses the direction. It's the same orientation of the vector, but the head of the vector went to the opposite side. So just reverse direction, okay? It's like we just turn it around. So the tip of A switches, it was here, now it's down here, okay? Pretty simple. Now, vectors multiplied by 0, the magnitude of the vector becomes 0. So that's just a 0 vector, and it's denoted by this. So remember that for whatever reason, I don't know why this prints like this on this screen, the file actually does have the arrow on top. So if you ever see that little dash, let me erase. If you ever see this little dash above something, that's supposed to be an arrow. I don't know why it does that. So this is an arrow above that. That's the 0 vector, okay? All right, so we have vectors A, 2A, and negative 3A. So here's the original A right here. 2A doubles the original A, still going in the same direction. Negative 3A triples the original A, but now it's reversed, okay? So the original A was pointed in that direction. 3A would be 3 times as long, but now because it's negative, we reverse the direction, so that's why we're going this way. Okay? All right, so now working with the vectors, if we have vector subtraction. So we have to subtract vector B from vector A. So what we want to do is think of vector B as like adding negative B to vector A. So here is vector B sitting right here, okay? Now if I just wanted to add A plus B, so if I wanted to do, just as an example, vector A plus vector B. Well, here's vector A, so I'm just going to kind of duplicate it over here. And then here's vector B, so I'm going to kind of duplicate it over here. Okay, so here's vector A, here's vector B, right? So what's the sum? Well, I start at where I started with vector A, and I go to where I finished with vector B. Here's A plus B. All right? They didn't ask us to do that. I just wanted to show you what that would look like. So now what's A minus B? Well, first of all, I got to figure out what negative B is. And then what I want to do is for A minus B, do A plus and then negative B instead. That's just easier, okay? Because plus negative something is the same thing as minus the same thing. So first, I want to think of B and then take B and make it negative B. So I just reverse the direction of B. And now I have negative B. So now I can set up A. Here's vector A. And now I can take negative B. There's negative B. And I'm adding them together. So there's A plus negative B, which in other words is A minus B, right? Mm-hmm. That's it, okay? So what I would probably write instead of what I just wrote is, get rid of that one too, A minus B.
Yeah.
Okay?
Oh,
Because that's what they wanted me to find, and that's what it is. That's your answer. Okay, so that's how you subtract those two vectors. So like I'm saying right here, imagine 5 minus 3 is the same as 5 plus negative 3. So there you go, okay? And that's what's happening down here. So we're good. And that is almost it. We're almost done. Here we go. Which figure shows 2p minus q?
I would say A.
You would say A?
Yeah.
Why?
Because you have twice as many for the P, so it doubles in length.
Okay.
And with the Q being negative, it would be flipped to the other side.
Very good. So 2p, we got to come up with double the p, right? So here is 1p, so I'm going to double that. Here's 2p. So we're going to double that vector. 2p's right there. Now negative q is going to reverse the direction. So q is actually now here, right? Negative q. And if I move this guy over to here by the parallelogram rule, there's my vector. It's A. Good job. So that's working with vectors, okay? It's not tough once you get the hang of it. If you don't have the hang of it at first, probably it's gonna seem tough, okay? So you just practice and you get the hang of it pretty quick. So that's it. That's the whole section already. We're done.